Welcome to Section 10, Hypothesis Tests regarding a parameter. Today we are going to look at Section 10.1. All right. So for each student in the class, I'm going to flip a coin. If the coin comes up heads, your grade in the class is the grade earned based on the syllabus. However, if the coin comes up tails, you automatically earn an A. Suppose the outcome of the first 5 students is heads, 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 and heads. What might you conclude? Based on the analysis above, you can make one of two conclusions. 1. The coin is fair, but just happened to come up heads 5 times in a row. Or 2. The coin is not fair. Are you willing to accuse your instructor of using a coin that is not fair? That is based toward flipping heads. This is the heart of hypothesis testing. An assumption is made about reality. We then look at sample evidence to determine if it contradicts or is consistent with our assumption. The big idea here is that we start by assuming something's true, like the coin is fair. Then we collect data to see if that assumption seems reasonable or if the data suggests otherwise. Oh, too far. All right, objective number 1. Determine the null and alternative hypothesis. So a hypothesis is a statement or claim regarding a characteristic of one or more populations. Hypothesis testing is a procedure based on sample evidence and probability used to test statements or claims regarding a characteristic of one or more populations. Think of it like a trial. We start with an assumption, innocent until proven guilty. We collect evidence, which is the sample data, and then we decide if the evidence is strong enough to change our minds. Now, the steps in hypothesis testing are 1, make a statement regarding the nature of the population. 2, collect evidence like the sample data to test the statement. And 3, analyze the data to assess the plausibility of the statement. Now, we need to understand why we use sample data. So we test these types of statements using sample data because it is usually impossible or impractical to gain access to the entire population. So if population data are available, there's no need for inferential statistics because we use sample data to test hypothesis. We cannot say with 100% certainty that the statement is true. We can only determine if the sample data supports the claim or not. We make an assumption about reality, then look at sample evidence to determine whether it contradicts our assumption. So that means we're making an educated guess based on incomplete information, the samples, not absolute statements based on complete information, which would be the population. So why does this matter? Well, since we're using a sample, not the whole population, there's always a chance our sample doesn't perfectly represent the population. This is why we can never be 100% certain. So we're working with probabilities, not certainties. So the null hypothesis, denoted H naught, is a statement to be tested that the value of a population parameter, which is mu, p, or sigma, is equal to some claimed value. The null hypothesis is a statement of the status quo, of no change, no effect, no difference, and is assumed true until evidence indicates otherwise. It always contains a statement of equality. So let me grab my pointer here. So these would be 3 ways in which we can represent our null hypothesis. Okay. I want you to think of H naught as the default position or business as usual, what we assume is true unless proven otherwise. So we always use an equal sign. the status quo. Things haven't changed. Okay. Some examples could be the new drug has no effect. So that would be mu equals the mean. Or the defendant is innocent. A person equals innocence. The coin is fair. So that means our P would equal 0.5. The average hasn't changed from what it used to be. Okay. Now, the alternate hypothesis, denoted H1 or HA, you can see it both ways, is a statement that we are trying to find evidence to support. It cannot contain equality, and it must be true if H naught is false. Okay, so think of H1 as we're trying to prove the challenger to the status quo. So we always use either the not equals, the greater than, or the less than. We never use the equal sign because the claim that something has changed is what H1 represents. So some examples for this would be the new drug does have an effect. So instead of it not having effect, it does. Or the defendant is guilty. The coin is biased. The average has then changed from what it used to be. So there are 3 ways to set up the null and alternative hypothesis. The first one is equal hypothesis versus not equal hypothesis, which is a 2-tailed test. Here, our H naught has a parameter equal to some value, and our H1, our alternative hypothesis, has a parameter not equal to some value. So we use this when we're testing if something has changed in either direction, whether it's increased or decreased. An example would be, is the average different from 100? Meaning the alternative would be, could it be higher or lower? The key words for this type of hypothesis testings would be different from, has it changed, not equal to. So think of it like this. If you're looking for any change, whether up or down, like asking, is my temperature different from normal, could be fever or hypothermia, you're checking for abnormality. Therefore, you're doing a 2-tailed test. The second is equal versus less than, which is a left-tailed test. So your parameter would equal some value for your null, and then your parameter would be less than some value for your alternative. So we use this test when we're testing if something has decreased. For example, is the average less than 100? Key words for this test would be less than, decreased, lower, fewer, reduce, decline. So you're specifically looking for just a decrease, like asking, has my blood pressure gone down since I started the medication? So you only care if it's decreased, not if it's increased. So then if the left tail test is for decreased, you can then assume, and you would assume correctly, that the right tail test, equal versus greater than, would be for increased. So this is where you have a parameter equal to some value for the null, and then a parameter greater than some value for the alternative. So we use this if we are testing if something has increased, like is the average greater than 100. So keywords for this test would be greater than, increased, higher, more, exceeds. So you're specifically looking for an increase, like asking, has enrollment grown? So that would mean you only care if it went up, not if it went down. All right. So let's now dive into some examples. But I also want to mention just a pro tip on how to identify which test to use. Um, Make sure that, and we'll do this here in this example, but make sure to read the question carefully and look for directional words. So if the researcher wonders if or tests whether something is different without specifying a direction, then we can assume that it's going to be a two-tailed test. And if they believe or suspect a specific direction, like higher or lower, we can then use that direction. Okay. So in this example, we're asked to determine the null and alternative hypotheses for each of the following, and then state whether the test is two-tailed, left-tailed, or right-tailed. So in the first one, according to the American Time Use Survey, the mean amount of time employed male Americans spend working on weekends is 5.46 hours. A researcher wonders if males employed part-time work more hours on average on weekends. Okay, so the key word here is more. Okay, that's the key word, more. Because the researcher is specifically looking for an increase, not just a change. So we know then that this is going to be a right-tailed test. Okay. Now, for our null hypothesis, mu will equal 5.46. Okay, so that is the mean for the hours spent on a weekend. We know we're using mu because our problem says mean, and the mean is 5.46. And we want to know if they spend more hours. So that would be the greater than sign for the alternative hypothesis. Greater than what? 5.46, which is the mean. We're trying to test whether the mean is actually greater than 5.46. Let's do the next one. All right, Harris Interactive reports that 55% of adult Americans aged 18 or over prefer purchasing name brand coffee over generic brands. A marketing manager with Starbucks wonders if the percentage of seniors who prefer name brand coffee differs from that all adult Americans. Okay, so in this example, the key word here is differs. Okay, differs. So this could mean the percentage is higher or lower than our 55%. So that means we're testing change in either direction. And since we're testing change in either direction, we are a two-tailed test. So here, 55% represents the proportion of adult Americans who prefer purchasing name brand coffee over generic brands. So P will equal 55. And since we're a two-tailed test, our alternative hypothesis is going to be P does not equal 0.55. So it could change in either direction, whether it's lower than that value or higher than that value. And then C, used in old marketing process, the standard deviation of the amount of wine put in a bottle was 0.23 ounce. With new equipment, the quality manager believes the standard deviation has decreased. So the key word in this problem is decreased. Okay, so the manager specifically believes it went down, not up. So we are going to do a hypothesis test for that. So to set it up, we know we're doing a left-tailed test because it is decreased. Our null hypothesis is going to be sigma because it says that the quality manager believes the standard deviation has decreased. So sigma equals 0.23. And since it's decreased, our alternative will be sigma is less than 0.23. All right, why don't you pause the video and attempt these three problems. All right, so hopefully you've attempted. Your directions here are just as the ones that we just walked through. So you want to determine the null and alternative hypotheses for each of the following, then state whether the test is two-tailed, left-tailed, or right-tailed. So for A, the level of giving has changed from the mean charitable contribution per household of 1,623. So your keyword here is changed. So it doesn't specify a direction, so that means it could be higher or lower. So this is a two-tailed test. So your null hypothesis will be mu equals 1,623, and your alternative will be mu does not equal 1,623. A school nurse thinks that the percentage of 6 to 11-year-olds who are overweight is higher than 16%. So the keyword here is higher than, which tells us we're specifically looking for an increase. So we're dealing with a percentage, so that is a proportion. So P is going to equal 0.16, and our alternative is going to be P is greater than 0.16 because our keyword higher than tells us that we are a right-tailed test. So we want to be increasing P, or we want to test whether P has increased. And C, a teacher believes that the standard deviation of SAT math scores has decreased from 113. So here our keyword is decreased. Decreased tells us we are specifically looking for it to go down. We are also dealing with the standard deviation parameter. So we are a left-tailed test due to the decreased term. And then we have our null as sigma equals 113, and our alternative sigma is less than 113. All right, objective 2, explain type 1 and type 2 errors. So when a decision is made in a test of hypothesis, there's a chance of making a wrong decision since it is based on incomplete sample information. These wrong decisions do not refer to human errors in sampling calculations, etc. They result from the fact that with real data, occasionally a sample can occur that leads to an incorrect decision. So the reality is that we're using sample data to make decisions about populations. So sometimes, just by random chance, our sample doesn't represent the population well, and we make a mistake. So think of it like this. If you flip a fair coin, you might get 8 heads in a row just by luck. That unusual sample might make you wrongly think that the coin is biased. That's not a mistake. You made it. It's just bad luck with the sample. All right, so we have 4 outcomes for hypothesis testing. So when we conduct a hypothesis test, there are 4 possible outcomes. The first one is to reject the null hypothesis when the alternative hypothesis is true. The decision would be correct. An example of this would be the defendant is guilty and we convict them, so justice served. The second, do not reject the null hypothesis when the null hypothesis is true. This decision would be correct. For example, the defendant is innocent and we declare them not guilty. So justice served. And the third, reject the null hypothesis when the null hypothesis is true. This decision would be incorrect, and this type of error is called a type 1 error. So the defendant is innocent, but we convicted them anyway. So this would be a wrongful conviction. And the fourth one, do not reject the null hypothesis when the alternate hypothesis is true. This decision would also be incorrect, and this type of error is a type 2 error. An example for this would be the defendant is guilty, but we let them go. Guilty person walks. So here we have our visual that summarizes our errors. Okay. So we have our conclusion here. Do not reject the null hypothesis or reject the null hypothesis, and the reality. So after the actual test, the null hypothesis is true, the alternate hypothesis is true. Depending on which one we have and which one our experiment gives us will then determine what our result will be. Okay, so you want to look at what the null hypothesis actually is, so the columns, the reality part, and then look at what you decide, which is the rows, which is the conclusion. So these cells tells you if you were right or wrong. Okay. So we illustrate the idea of type 1 and type 2 errors by looking at hypothesis testing from the point of view of a criminal trial. In any trial, the defendant is assumed to be innocent, so we give the defendant the benefit of the doubt. The district attorney must collect and present evidence proving that the defendant is guilty beyond all reasonable doubt. Because we're seeking evidence for guilt, it becomes the alternative hypothesis. Innocence is assumed, so it is the null hypothesis. So the null is the defendant is innocent, the alternative, the defendant is guilty. So in a trial, the jury obtains information, which is the sample data. It then deliberates about the evidence, the data analysis, and then finally, it either convicts the defendant, rejects the null hypothesis, or declares the defendant not guilty, fails to reject the null hypothesis. Note, and this is important, the defendant is never declared innocent. That is, the null hypothesis is never declared true. The 2 correct decisions are to declare an innocent person not guilty or declare a guilty person to be guilty. The 2 incorrect decisions are to convict an innocent person, which is a type 1 error, or to let a guilty person go free, which is a type 2 error. So it is helpful to think in this way when trying to remember the difference between a type 1 and a type 2 error. So just like in statistics, in court, we never prove innocence. We only say not enough evidence for guilt. Similarly, we never prove the null hypothesis is true. We only say not enough evidence to reject. So here we have our visual of a criminal trial, of our criminal trial analogy. So in other words, a type 1 error is like putting an innocent person in jail, and a type 2 error is like letting a guilty person go free. So when we think about the consequences of these errors, they can be rather significant. So for a type 1 error, an innocent person goes to prison, meaning we have rejected the null when it was actually true. So in our justice system, this is considered the worst error. We said guilty when they were actually innocent. Then for a type 2 error, a guilty person walks free. So that means we failed to reject the null hypothesis when the alternate hypothesis was actually true. We said not guilty when they were actually guilty. The criminal goes unpunished. So which is worse then? In criminal justice, we consider type 1 errors worse, convicting an innocent person. So we set the bar very high, beyond a reasonable doubt. In statistics, we control type 1 errors by setting alpha to a small value like 0.05. All right. So when we studied intervals, we learned that we never know whether a confidence interval contains the unknown parameter. We only know the likelihood that a confidence interval captures the parameter. Similarly, we never know whether the conclusion of a hypothesis test is correct. However, just as we place a level of confidence in the construction of a confidence interval, we can assign probabilities to making type 1 or type 2 errors when testing hypotheses. So the parallel here is that confidence intervals, we're 95% confident, but we might be in that unlucky 5%. Hypothesis tests, we control our error rates, but we might still make a mistake. So the following notation is commonplace. So alpha equals P, the probability of a type 1 error, which is equal to the probability of rejecting the null when the null is true. And then beta, which is the probability of a type 2 error, is the probability of not rejecting the null when the alternative is true. Okay. Now, what does all of this mean? Well, alpha here is the probability that we make a type 1 error. So consider that like a false alarm. Okay. And we choose this value. We choose this alpha value, which could be 1%, 5%, 10%. It's the significance level of our test. Beta here is the probability that we make a type 2 error. So we miss a real effect. This is harder to control, and it depends on many factors. All right, so it's related to power. Usually we take 1 minus beta, which is equal to the power of the test. So the trade-off here is that if you make a small alpha, meaning you're more cautious about rejecting the null, then beta gets larger, more likely to miss a real effect. It's like adjusting a metal detector sensitivity. Turn it up and you get false alarms. Turn it down and you miss real metals. Okay. So the level of significance, alpha, is the probability of making a type 1 error. So by setting alpha very small, like 0.05, for example, we are indicating that we're willing to accept this error only 5% of the time. Setting the alpha level involves the seriousness of the type 1 error. In some cases where the type 1 error is not so serious, alpha might be set at 0.10. A type 1 error with more serious consequences might mean an alpha of 0.01. As the probability of type 1 error increases, the probability of type 2 error decreases. Okay. So let's see. So I just want you to think of this level of significance as, let's think of it this way. So we're setting alpha equal to 0.05, which means we're saying I'm willing to be wrong, make a type 1 error, falsely rejecting the null 5% of the time. That's what alpha equaling 0.05 would mean. So in other words, if we ran this test 100 times and the null was true every time, we'd expect to incorrectly reject it about 5 times. Okay, so that's what the level of significance would mean. All right, objective number 3. State conclusions to hypothesis tests. Okay, so how do we state our conclusion? So once a decision whether or not to reject the null hypothesis is made, the researcher must state his or her conclusion. So it is important to recognize that we never accept the null hypothesis. So we never say accept null. We only say reject null or do not reject the null. This matters because it makes a huge difference between we don't have enough evidence to convict, do not reject the null, to we have proven innocence. This would be accepting the null, and we can't do that. So again, the court system analogy helps us to illustrate the idea. The null hypothesis is the null is innocent. So when the evidence presented to the jury is not enough to convict beyond all reasonable doubt, the jury's verdict is not guilty. Notice that the verdict does not state that the null hypothesis of innocence is true. It states that there's not enough evidence to conclude guilt. This is a huge difference. Being told that you are not guilty is very different from being told that you are innocent. Okay, so key distinctions here. Not guilty, which is the verdict, does not equal innocent, the claim of truth. Do not reject the null, the statistical decision, is not the same as the null is true. That's the claim of truth. Okay, we just got to make sure that we understand that. One real world example is just coming to mind is the O.J. Simpson case. So O.J. Simpson was found not guilty in criminal court. This doesn't mean the jury proved that he was innocent. It means that they didn't have enough evidence to convict beyond a reasonable doubt. And that's exactly how hypothesis testing works. So sample evidence can never prove the null hypothesis to be true. By not rejecting the null hypothesis, we're saying that the evidence indicates the null hypothesis could be true. That is, there is enough evidence to reject our assumption that the null hypothesis is true. Just remember, sample evidence can never prove the null is true. We can only say there's not enough evidence to reject the null. This is a subtle but very, very important distinction. And why can't we prove the null? Well, we're using a sample, not the whole population. So maybe with a different sample or a larger sample, we find evidence against the null. So the best we can say is, based on this sample, we don't have enough evidence to reject the null. Okay. All right. So an example, the Graduate Record Examination, GRE, is a test required for admission to many U.S. graduate schools. Student scores on the quantitative portion of the GRE follow a normal distribution with a mean of 150. An admissions officer at a large graduate school believes the mean is less than 150. Okay. So the keyword here is less than. And because we know it's less than, we know it's a left-tailed test. So our null hypothesis is going to be mu. We're dealing with the mean is equal to 150, and our alternative is mu is less than 150. Okay, explain what it would mean to make a type 1 error, and then we'll explain what it would mean to make a type 2 error. So the type 1 error would be that the mean is 150, but the sample evidence suggests the null hypothesis should be rejected. Okay, so in plain English, this would mean that we can conclude that the mean is less than 150, but in reality, it's actually 150. So we falsely claimed it decreased. Okay, so in the context of our problem, the admissions officer would wrongly believe that current students are scoring lower than the national average, when in fact they're scoring right at the average. This might lead to unnecessary changes in admissions policies. Okay. Now, the type 2 error. Okay, so for type 2 error, the mean is less than 150, but the sample evidence suggests that the null hypothesis should not be rejected. So in translation, the mean really is less than 150, but our sample didn't give us strong evidence to detect this, so we missed it. So in the context of our problem, the admissions officer would fail to detect that their students really are scoring below the national average, missing an opportunity to address a real problem. Next example. Many healthcare workers believe the mean body temperature of healthy adults is 98.6 degrees Fahrenheit. Philip A. McElwack, a doctor at the University of Maryland for Center for Vaccine Development, suspects this number might be incorrect. Okay, so the key word here is suspects. All right, so the doctor suspects it might be incorrect, but he never specifies if he thinks it's higher or lower. He's just testing whether it's different. So that means our test is going to be a two-tailed test. Since we're dealing with the parameter mean, we will use mu equals 98.6, and mu does not equal 98.6. Okay. B is asking us, sample data indicated that the null hypothesis should be rejected. State the conclusion of the researcher. So there is sufficient evidence to suggest that the mean body temperature of healthy adults is not equal to 98.6 degrees Fahrenheit. Okay. Note the careful wording. We suggest, not prove. We say not equal to, because that's what our alternative hypothesis is claiming. Not equal to 98.6. Okay. And C, suppose the mean body temperature of healthy adults is actually 98.6 degrees Fahrenheit. Was a type 1 or type 2 error committed? Well, this would be considered a type 1 error. Why? Because we rejected the null, claiming that the mean is not 98.6, but the null was actually true. The mean really is 98.6. So we had a false alarm. We thought we detected a difference when there wasn't one. Okay. So the real world consequence of this problem is that the medical center or community might change their understanding of normal body temperature based on the study, when in fact the old standard was correct all along. All right, why don't you pause and attempt this practice problem? All right. So for your practice, pork producers and their neighbors are concerned about potential health safety and environmental issues associated with swine barns. The Veterinary Infectious Disease Organization conducted a 5-month air quality study and found that there was no statistical significant increase in airborne pollutants 600 meters downwind from a swine barn. Let X be the increase in airborne pollutants measured 600 meters downwind from the swine barn. Okay. So in this problem, our key word here is increase. So we're testing if there's an increase in pollutants, not just any change. So we are going to have a right-tailed test. Okay. All right. So mu here is going to equal 0 for our null, and then mu will be greater than 0 for our alternative. Okay. So the sample data indicated that the null hypothesis should not be rejected. State the conclusion of the researcher. So there is insignificant evidence to suggest that there is an increase in airborne pollutants 600 meters downwind from a swine barn. Note here that we say insufficient evidence, not prove there's no increase. Big difference. Now, suppose in fact there is an increase in airborne pollutants 600 meters downwind from a swine barn. Was a type 1 or type 2 error committed? So this would be a type 2 error. Okay. Why? Well, we failed to reject the null, claiming no increase. But the alternative was actually true. There really is an increase. So we missed detecting a real problem. So the real world consequence would be that people living near the swine barns might not take protective measures because the study said there's no increase, when in reality, there is an increase in pollution affecting their health. Okay. All right. And that concludes section 10.1.